Yeah, so I will just give proofs of some of the results that I mentioned last time. Okay. About this paper of Werner and Wolf, bound entangled Gaussian states, this 2001 PRL paper. Okay. Okay. So, what I discussed last time is that if you have, so let us say rho A B, which is a state, which is a product state, rho A tensor product rho B of an n plus m mode system. So, this n belongs to the subsystem A, n number of modes, and this m belongs to the subsystem B. Okay. So, this is a product state. So, in that case, what we have proved is that the covariance matrix of rho A B, which is the covariance matrix of rho A tensor product rho B, which is covariance matrix of rho A direct sum covariance matrix of rho B. So, this we have proved. Okay. So, this is what we have proved. Next, we assume that uh, uh, rho A B is a Gaussian state with covariance matrix gamma rho A B is equal to gamma A direct sum gamma B. So, this is a valid or bona fide covariance matrix for A, and this is bona fide covariance matrix for B. So, it is not necessary that this is the, I mean this is the covariance matrix of the reduced density matrix of A, and this is the covariance matrix of reduced density matrix of B, but these are valid covariance matrices. So, this is a this is a Gaussian state n plus m mode for which its covariance matrix is of this form. Okay. Then, so then the Wigner function, because this is Gaussian state. So, the Wigner function of rho A B of this R. So, this R is now an element of r to the power 2 n plus m, and this I can write as R A direct sum R B, right, where R A is an element of r to the power twice n and R B is an element of r to the power twice m, right. This is how I can write. Okay. So, then I know that because this is a Gaussian state, so I can write it as 1 upon square root of determinant of gamma rho A B, then exponential of minus half, this is R minus R hat, this is rho A B transpose into gamma rho A B inverse, then R minus R hat rho A B, right. This is the Gaussian Wigner function, okay, because this is a Gaussian state. Okay. So, you can now use this form that this is your covariance matrix. So, what I can write therefore is that this thing is equal to 1 upon square root of determinant of gamma A into determinant of gamma B, right, because of the direct sum result. And then this will be into exponential of minus half. Now, I will split it into this R A direct sum R B. So, I can write it as R A minus R A hat. This is with respect to, you can write rho A B, but ultimately we will see that. So, transpose, then see when it is a direct sum, then inverse of this is equal to inverse of this direct sum inverse of this, right. So, therefore, this will be gamma A inverse, then R A minus R A rho A B, and then minus half, this is R B minus R B, this rho A B, this is transpose, and then gamma B inverse, then R B minus R B rho A B. Okay. So, this is how we can split it because of this thing. Okay, right. So, if you now remember the expression of Wigner function, Gaussian Wigner function, then this is nothing but the Wigner function of yeah. So, this I can call as the Wigner function W A of R A transpose W B of R B transpose, right, because this part will give you the 1 by square root of determinant of gamma A times this exponential will give you W A R A and times W B R B. Okay. Okay, good. Now, so this is what? This is basically, if you look at it, so this part basically, if you look at it, this W A R A transpose, this is nothing but W of rho A. So, you take this Gaussian state and then take its reduced state, because this is Gaussian, its reduced state is also Gaussian, both rho A and rho B, and therefore, its Wigner function will be also Gaussian. So, this is a Gaussian Wigner function, this is also Gaussian Wigner function, and so this is R A transpose. Similarly, W B, so W B R B transpose is nothing but rho B. So, this is the reduced state of R A B transpose. Okay. So, what you have obtained is that if you have a Gaussian state rho A B for which the covariance matrix is in the direct sum, then your, so this will imply that the covariance the Wigner function of this thing is nothing but product of the Wigner functions. Okay. So, this is what you can see, right, and this means that because this is the at Wigner function, because the Wigner function and states are in 1-to-1 correspondence. So, this will imply that your state rho A B is basically rho A tensor product rho B, because otherwise this will not happen, because it happens at the Wigner function level. So, you see that if for a Gaussian state this happens, then the state must be a product state, and what we have seen is that if original state is product state, Gaussian or not, I do not care, then its Wigner, then its covariance matrix is just direct sum. Now, here it is kind of opposite, not exactly opposite, kind of opposite. It says that if the state is Gaussian, then satisfying this condition means that the state is tensor product and product state. Okay. Good. So, now let us go to this proposition 1 which I just mentioned last time. It says that let gamma rho A B be the covariance matrix of an n plus m mode separable state. Rho A B, okay, having finite second moments, that is okay. Right. So, this is a covariance matrix of a separable states rho A B, right. Then there exists covariance matrices gamma A and gamma B such that gamma rho A B is greater than or equal to gamma A 0 0 gamma B, which is simply means that this is gamma A direct sum gamma B, right. This is same as this. Okay. So, this is the part 1. So, it says that if rho A B is a separable state, then you can figure out this covariance matrices gamma A gamma B such that this is satisfied. Now, the conversely, which I will call part 2. So, conversely, so let me call these as this condition as let us say 1, condition 1. Okay. So, conversely, if condition 1 is satisfied, okay, by the covariance matrix gamma rho A B of an n plus m mode Gaussian state rho A B, then rho A B is separable. So, if this condition is satisfied, we cannot say directly that rho A B is separable, but if I know that this condition is satisfied for a Gaussian state, then I can show that the Gaussian state is separable. Okay. Right. So, let me go through the proof. I will not go proof of part 1. So, where we are going to show that for a separable state you can find out gamma A and gamma B such that this is satisfied. Okay. Right. Okay. So, rho A B is separable, this is given, right. So, this means that rho A B I can write it as sum over k lambda k, this is sigma A k tensor product, let us say eta b k. So, these are, so lambda k's are, this is a probability distribution. These are the states of A subsystem, these are states of B subsystem, okay, because this is separable. Okay. So, now you know that if I look at, let us say, the j kth entry of this. So, j and k take values from 1, 2, 3 up to 2 n plus m, right. This is thing. So, if I now look at this j kth entry, or let us say I call it as j k prime entry, or whatever you want to call it, it is not a problem. Okay. So, this I know that by definition this is trace of rho a b times half the anti-commutator of r j and r k prime, okay, right, minus mean value of r j with respect to rho a b times mean value of r k prime with respect to rho a b. That is the usual definition. So, yeah, so now if I use all this thing, okay. So, what you will get, I am not going into all the details. So, this is the anti-commutator, half times the anti-commutator. So, what you will see is that this will tell you that let us call it as delta j k prime, which is defined as gamma rho a b j k prime minus sum over k lambda k gamma sigma a k direct sum gamma eta b k. You remember that if you have a product state, then the covariance matrix of this is just the direct sum. Okay. So, this quantity, this is my definition, and from this relation you can see that this will be sum over k lambda k r j, then this is sigma a k, because I am taking k, I have taken k prime here, but that is okay, tensor product eta b k, okay, then dot r k prime, again sigma a k tensor product eta b k, okay, minus sum over k and L lambda k lambda L r j, this is sigma a k tensor product eta b k times r k prime sigma a k tensor product eta b k. Yeah. So, basically this is the quantity I define. So, this is what? This is, yeah. So, difference of these two, which I call delta j k prime, which turns out to be from this relation like this, difference of these two quantities, okay, right. So, this is basically the delta is the difference between original covariance matrix and then some block diagonal covariance matrix, okay, right. Okay. And now, now you can so if we look at the expression for delta, you see that this is a real symmetric matrix, these are also real symmetric matrices and these are this is probability. So, this will be as a whole real symmetric matrix. Okay. Right. So, this delta is a, so what is the size of this? Yeah, 2n plus 2m cross 2n plus 2m real symmetric matrix. Okay. Okay. In fact, you can prove, which is not difficult, that this is moreover this delta is greater than equal to 0. So, this is positive semi definite. Okay. It is not difficult, you can one can prove it directly. So, basically what you need to look at is I take this vector r, any vector in r to the 2n plus 2m, and I will have to show that r transpose delta r is greater than equal to 0. That will show that this is a positive semi definite. So, I am not going to do that. So, you can basically what you can prove is that this quantity, so this quantity is equal to half times sum over k and L, lambda k lambda L, this is S k minus S L whole square, because these are probabilities and these are real numbers whole square. So, this is greater than equal to 0 and what is, so this means that delta is greater than equal to 0 and what are these S k S L? So, this okay. So, S k, if I look at it, S k is sum over j. So, this j is equal to 1 to twice n plus twice m, and here this k and L runs for the how many probabilities are there. So, this is R j is the jth entry of the quadrature variable times m j into k. Okay. And what is this m j? M j is m j k, this is equal to R j, its expectation value with respect to this product state which appeared there. Okay. So, this is how you define things. Okay. So, yeah. So, from here you see that delta is greater than equal to 0, is a positive semi definite matrix, and yeah. So, that will do the job. Okay. So, now we need to, so we are proving this part 1. So, what we need to prove, that we have to figure out this gamma A and gamma B covariance matrices such that this condition is satisfied, assuming that this is a separable state. Okay. So, now if I look at this part, which is basically this one, this part. Okay. So, this is sum over k lambda k gamma sigma k sigma a k, then direct sum gamma eta b k, right, that is what it came. Yes. So, this as I discussed earlier, that I can, because this is direct sum, I can take it like this, sum over k. So, this is lambda k gamma sigma a k, direct sum lambda k gamma eta b k, right. This I can always do. Yes. And so, because this is direct sum, so I can just sum of this k gamma sigma a k, this sum plus direct sum k lambda k gamma eta b k. Okay. And this is nothing but gamma of basically trace over B of rho A B, right, because this part if you take the separable state, this is the reduced state plus gamma then trace over A rho A B. Okay. So, which is gamma of rho A direct sum gamma of rho B, okay, right, and you call this as gamma A and this as gamma B, right. So, from there you see that delta is equal to gamma rho A B minus gamma A direct sum gamma B, right, and this is greater than equal to 0 because delta is greater than equal to 0. So, therefore, this part is proved. So, 1 is proved. Okay. Right. So, next I will prove this part, that this condition is satisfied by the covariance matrix of a Gaussian state, and then I will prove that the state is separable. Okay. So, this is proof of part 2. So, this I assume that rho A B is a Gaussian state for which condition 1 is satisfied. We will have to show that rho A B is separable. Okay. Right. So, let us assume that, see, this gamma A and gamma B, these are valid covariance matrices, right, because that is by assumption, these are valid covariance matrices. So, let us assume that this, what is it called, xi or chi, whatever, xi is equal to xi A tensor product xi B be a Gaussian product state, right, such that gamma of xi A B is equal to gamma of xi A, which is of course true because this is a product state. So, this is xi A gamma of A plus gamma of B, where gamma of A is equal to gamma of xi A and gamma of B is equal to gamma of xi B. Look, when these are covariance matrices, I can always choose a Gaussian state for this and a Gaussian state for this. It is a density matrix, yes. This is a Gaussian state which is tensor product of two Gaussian states. Okay. This is why Gaussian product state. So, I assume that this is the covariance matrix of this Gaussian state xi A and this is the covariance matrix of this Gaussian state, and therefore, the covariance matrix of their tensor product is just the direct sum. Okay. So, let us take gamma prime to be gamma of rho a b minus gamma a direct sum gamma b. So, rho a b is a given state, right, the original Gaussian state, right. So, because of the assumption this condition 1, so this condition 1, this implies that gamma prime is positive semi definite, right. In fact, one can prove that this gamma prime is the covariance matrix of a classical Gaussian probability distribution. On the phase space on the 2 into n plus 1 dimensional you can say phase space also, phase space P, which I call P. Okay. So, this is covariance matrix of a classical Gaussian probability distribution. Okay. So, why is it so? I mean, I am not claiming that this is a bona fide covariance matrix of a, that means it corresponds to the covariance matrix of a quantum state. What I am claiming is that this is a covariance matrix of a classical Gaussian probability distribution. Okay. So, why is it so? The proof of this. So, let me prove this part first. Okay. Okay. So, let us consider this part. So, P prime is that part of this P entire phase space on which gamma prime has positive definite eigenvalues. Understand? So, because this is non-negative, some of the eigenvalues of gamma prime can be 0. So, I am considering only those part which I am calling P prime of the entire phase space for which gamma prime has positive definite eigenvalues. Okay. Right. And in that case, you see that, so in that case what happens? Because then I can of course take this this distribution function. For example, this I will call this as, let us say, P of r. This is my probability distribution, which is 1 by now I mean okay. So, this is determinant of gamma prime times exponential of minus half, you can take this r minus some mean value. Okay. So, I should not call it like this. So, maybe some mean value. Okay. So, this is mean value. So, this is mean value which we can get from gamma prime transpose gamma prime inverse r minus this mean value. So, where this r belongs to this P prime. So, you see that this is a valid probability distribution and this is of course Gaussian, okay, and this is a classical probability distribution. So, this is a classical Gaussian probability distribution. I am not claiming that gamma prime plus iota by 2 omega greater than equal to 0. I am not claiming that. Okay. This may be true, may not be true, but this is of course true, because I am concentrating on only that part of the phase space on which this has positive eigenvalues gamma prime. Okay. So, therefore, this will give rise to a bona fide probability distribution, and now you can extend it, extend this P to P. How do you do that? So, you define P of R transpose is equal to 0 for all R belonging to P minus P prime. Right. Whenever you have R which falls beyond this P prime, you take the corresponding probability to be 0. Okay. Right. Okay, good. Okay. So, then so now let us look at the, so let me erase this part. So, the characteristic function. So, characteristic function which I will call rho of A B of R P, the characteristic function of this density matrix, because if I know the characteristic function, I will do the Fourier transform on it to get the Wigner function. So, this characteristic function is given by exponential of iota, this is the mean value of this rho A B. So, I am not writing rho, but basically this is rho A B transpose, then this is R. Okay. So, this has to be R, R transpose, right. Okay. R minus half, this is R transpose gamma rho R. So, at the characteristic function level also this is Gaussian. So, this is the characteristic function, and if you want to use this gamma prime and then your Gaussian state that I have taken originally. So, this is xi A B is equal to xi A tensor product xi B, this is Gaussian such that gamma A is equal to gamma xi A and gamma B is equal to gamma xi B, where gamma A, gamma B are given in that equation, equation 1. Okay. So, what you can do, you can use, so this is your mean value. So, what you can do is that you can now write it using this expression for gamma prime and this classical probability distribution, is that this is the characteristic function of the xi, which I have written. I mean, unfortunately, this will also look like rho, but this is not rho, this is xi. Okay. So, the characteristic function of xi, okay, at this point R. So, this is the product Gaussian state multiplied by Fourier transform of P of R t. So, you see this is P of R t, where I have this is the Gaussian classical Gaussian probability distribution. Okay. So, if you split everything here, this is what you will get, right. So, it is characteristic function of this product Gaussian state times Fourier transform of your classical Gaussian probability distribution, right. So, what does it mean? It means that your basically this is at the characteristic function level. So, this means that this rho a b original Gaussian state that we started with, this is actually convolution of, because its characteristic function is the product of this. So, this will be convolution of this xi a b, which is the product Gaussian state, and P of R transpose. So, this is the characteristic function of classical Gaussian probability distribution. Yes, yes. So, you see that the characteristic function of the given Gaussian state rho, which is not necessarily separable, I am not assuming anything. This can then be written as that because I have used this property. So, you can write it as characteristic function of the product Gaussian state times characteristic function of the classical Gaussian probability distribution, and this means that your original state rho, that means this state, has to be convolution of this product Gaussian state and the probability distribution. Okay. And this you can, this was you can look for proof of this as in, this is in RF Warner Journal of Mathematical Physics, volume 25, and then page number 1404, 1984. Okay. Right. So, what does it mean that this is a convolution? It means that your rho a b is basically, you take this R from your entire phase space, which I am calling P, entire phase space of d of R, then P of R, P of R transpose, it does not matter, and then when you do the convolution of this state, so the convolution will depend upon R, choice of R. Okay. So, you choose R with this probability, which is the classical Gaussian probability, and then you convolve. So, this convolution is basically your Weil transformation, that means the displacement, phase space displacement, R transpose, d of R transpose, this is xi a b, and then d of R transpose dagger. So, this is your, this is the phase space displacement, okay, Weil operator. This is the phase space displacement. So, what are you doing? You are displacing your product Gaussian state through this amount, and the choice of R depends upon this classical Gaussian probability distribution, and then you take the average. Okay. Right. Now, you know that this displacement is a local unitary transformation, because this displaces the first phase space like x 1 p 1 component, then x 2 p 2 component, x 3 p 3 component, etc. right. So, this does the displacement separately on the individual 2 dimensional phase spaces. So, therefore, this is a local unitary transformation, and this is also a local unitary transformation, and this is a product state. So, therefore, this as a whole is a product state. In fact, it is not just a product state, this is a Gaussian product state, because displacement does not change the Gaussian property. So, this is a Gaussian product state, and you are averaging over a Gaussian probability distribution. So, therefore, this tells you that this is a separable state, because this is convex combination of product states. So, therefore, rho a b is separable. Okay. So, this is a specific separable state this is a Gaussian mixture of product Gaussian states. Okay. So, therefore, this is separable state. So, we have now proved this proposition 1. Okay. So, remember this is a Gaussian state. So, this is a separable Gaussian state, it turns out to be separable. So, separable state I can of course write as convex combination of tensor products of states. So, here it turns out that this is a Gaussian mixture of tensor product of Gaussian states. Okay. So, yeah, and that is not, that is a very special case, I can write this separable Gaussian state as a convex combination of Gaussian probability distributions of, involving Gaussian probability distributions of product Gaussian state. That is a very, very special case. Okay. Right. Okay, good. So, now let us, yeah, I will not, so this I have already discussed about the partial transposition and all that. I am not going to do that. Let me see. Yeah. So, next part is this. So, this was about this proposition was about separable Gaussian state, separability problem. Basically it is about separability of states. Now, let us go a bit further, let us go for PPT states. Okay. So, this is proposition 2, this I also mentioned in my class. So, it has part 1 which says that let gamma rho A B be the covariance matrix of an n plus m mode state rho A B having finite moments, well, finite second moment is okay, but finite moments. Okay. Let this rho A B T A is greater than or equal to 0. So, it has a positive partial transposition, right. Then gamma rho A B plus iota by 2. Now, I am taking this, you apply the partial transposition corresponding transformation in the phase space. So, this omega, it will go to omega lambda, which I call as lambda tilde, and this lambda tilde we know that in this case it will be minus lambda plus this, because generally this is this plus this, right. Okay. Right. So, this then minus omega A plus omega B greater than or equal to 0. So, because of this positivity of partial transposition. Conversely, so this is again part 2, this says that if gamma rho A B plus iota by 2 minus this plus this greater than or equal to 0 for an n plus m mode Gaussian state rho A B, okay, then rho A B T A is greater than or equal to 0. So, you see this is somewhat generalization of this proposition, where you replace separability by positive partial transposition. Okay. Yes. So, this is basically the idea. Yeah. So, this part I do not have to prove. So, proof of part 1, this we have already discussed several times, that if this is the covariance matrix of a state, and if its partial transposition is positive semi definite, that means this is also a valid density matrix, then of course this is true. So, I do not have to prove anything, this is already done. Okay. So, let us look at proof of part 2. Okay. So, what is that? So, assume that rho a b is a Gaussian state, okay, such that gamma rho a b plus iota by 2 minus this plus this greater than equal to 0, right. This is the condition. So, we will have to prove that this is positive semi definite, it has positive partial transposition. Okay. Now, look at this condition, we know that this is equivalent to gamma rho a b plus P a plus I by 2 omega greater than equal to 0, right, because that is the way we have seen. Okay. Right. So, now okay. So, because this is Gaussian, so rho a b is Gaussian, that is given. So, this will imply that the Wigner function is also Gaussian. So, which is 1 upon square root of determinant of rho a b, determinant of gamma rho a b into exponential of minus half, this is r minus r hat rho a b transpose gamma rho a b inverse, then r minus r hat rho a b, right. This is the Gaussian state. Okay. Yeah. So, if I now look at the partial, the Wigner function of the partially transposed state. Okay. So, this I know that this is the Wigner function of lambda r transpose, where this lambda, you know that lambda is equal to diagonal, because on the A side I am doing 1 minus 1, 1 minus 1, 1 minus 1, this is 2 n modes, and then 1 1 1 1 1 1, this is 2 m modes. Okay. This is my lambda. Okay, good. So, So, if you now use this expression, what you will get is basically the following: 1 upon determinant of gamma rho a b into okay. Now, yeah, so there will be some issue here, but that is okay. I mean, this is yeah, so this is exponential of minus half r minus r vector rho a b, then gamma rho a b inverse, no, not rho a b, gamma t a inverse, this is r minus r vector rho a b. Okay. So, how do you get this? Basically, this rho a b t a inverse, this is equal to lambda gamma rho a b lambda inverse. Okay. So, from there you will get this. Okay. So, you use this relation, this is how you get it. Okay. Right. So, this is of course a valid Gaussian distribution. Of course, one should be a bit careful, because this is a, because you see I mean, there will be an issue with the normalization, but that is okay, that is fine. But up to normalization, this is of course a valid Gaussian probability distribution. Why? Because you see, this is positive, this gamma is positive, and then I am, what is lambda? Lambda is a unitary transformation, right. So, therefore, this is a basically similarity preserving transformation. So, this does not change the positivity, and therefore, I can take its inverse. So, this is a positive positive definite matrix, okay. And therefore, this is a, I mean, valid Gaussian distribution modulo this normalization, but that is okay, right. Yeah. So, therefore, you see that now this normalization factor, this is basically the normalization of the state, nothing else. So, therefore, you see that this is a bona fide Gaussian distribution, Gaussian probability distribution, or you can say, because this is in this Wigner form. So, this is a Wigner distribution function of a bona fide state, right. Okay. So, as a result, you can say that rho a b t a, this is a bona fide state, right, because otherwise its Wigner distribution, how can it be a Gaussian one? Okay. So, this is a bona fide state, and this means that rho a b t a, this has to be greater than or equal to 0, because otherwise it is not a state. Okay. So, this shows that we have also proved the converse, which says that this is, if it is a Gaussian state, then this is positive semi definite. Okay, good. Okay, so now what is the time? The finally I will go to the proposition 3, but before that I will have to.
What would be a typical example of bound entangled state in real systems? Is it like the two photon bound state in an array of two level atoms in a waveguide? Would that correspond?
Not exactly so. I mean, in fact, some people have done the realization of these bound entangled states. Okay, so I'll have to look into it, but but as I said, this is a very rare phenomena. Okay, so it is not unlike in the discrete variable case, you don't get to see it often. Yeah. I mean, this idea of bound states, I don't think it has anything to do with the bound entangled state here. Okay, so there is some definition which I will require later, which is that so this is gamma is a 2n plus m cross 2n plus m real symmetric matrix. Okay. Gamma is PPT covariance. Okay, this is called PPT covariance. Okay, if and only if gamma plus iota by 2, this is greater than equal to 0, and gamma plus iota by 2 tilde is greater than equal to 0. What does it mean? It means that if gamma corresponds to the covariance matrix of a state rho a b, then rho a b partial transpose is also a valid density matrix. Okay. So, a PPT covariance matrix gamma is minimal. So, we say that a PPT covariance matrix is minimal. There is minimal PPT covariance. Okay. If for any other PPT covariance matrix gamma prime with gamma less than equal to gamma prime, we must have gamma is equal to gamma prime. What does it mean? It means that this is the minimal PPT covariance matrix. Okay. You cannot have something less than that. Okay. So, with this definition, one can now prove that. So, this is, you can say, some remark or whatever. It tells that a minimal PPT covariance matrix gamma corresponds to the covariance matrix of a separable state rho a b. Here I am not saying that this is of course dimension 2n plus m cross 2n plus m, which so this corresponds to the covariance matrix of a separable state if and only if gamma is equal to gamma a direct sum gamma b, which is basically gamma rho A, direct sum gamma rho B. Okay. Yeah. So, and in fact, this is gamma of rho A tensor product gamma of rho B. So, you see that so this minimal PPT covariance matrix corresponds to the covariance matrix of a separable state if and only if its covariance matrix is of this form. Okay. Right. So, I am not going to prove this thing, this can be proved, it is not difficult. Okay. So, now let us, yeah. So, here is the proposition 3, which I am not sure whether I will have time to prove, but let us see based on these definitions. Okay. So, basically it tells you that once you know your covariance matrix is minimal PPT, then you can talk about the separability of the state. Okay. So, that is what it tells you. So, this proposition 3 let gamma be a PPT covariance matrix. Let n be the null space Gaussian of gamma plus iota by 2 omega and n tilde be the null space of gamma plus iota by 2 omega tilde. Okay. You know, by definition both of these are non-negative, because this is a PPT covariance matrix. Okay. Then gamma is minimal if and only if you remember we have defined this real part of this. So, real part of this means you take the real part of those vectors in the null space of this, okay, and the linear span of this, that will be this. So, this union real part of n tilde. So, if and only if this spans the entire phase space, which I have called P, P. Okay. So, this is minimal if and only if this is the case. Okay. Yeah. So, the proof of this is, of course, one can prove it, but yeah. So, let us see. Yeah, it is actually too much, you know. Yeah, maybe I will skip this because this proof is there in the paper. Okay, so same paper, Wolf and yeah. So, this is there. So, basically I will tell you the I mean, if a covariance PPT covariance matrix is not minimal, how to bring it to a minimal form, that is the essential part. Okay. So, that will be used in this proof. So, I am not going to prove this thing, but this provides you a criteria to check minimality of PPT covariance matrix, right. So, this provides you criteria. So, let us say that that gamma is a PPT covariance matrix, right. Let us assume that this is PPT covariance matrix, but not minimal. Okay. So, what does it mean? It means that, so this implies that there exists another PPT covariance matrix gamma prime less than equal to gamma, such that gamma prime is not equal to gamma, right, because for minimal it is same, right. So, now let us define this delta, which is gamma minus gamma prime. This is my definition. So, obviously, because of this condition, this is greater than equal to 0, and if I look at rank of delta, you know, it can be, I mean, interesting part will be if it is less greater than equal to 1 and less than equal to rank of gamma, right, because rank of delta cannot be greater than rank of gamma, and minimum it can have is 1, right. Okay. So, now what you can do is, let us say that you take this delta and take a spectral decomposition. Which is sum over L is equal to 1 to rank of delta, okay, mu L, this is psi L, psi L. So, these are the eigenvectors of delta and these are the eigenvalues, okay. And of course, these mu L's are greater than 0, because this is a positive, when I talk about rank, none of the eigenvalues will be 0, it will be all positive, right. So, now what you can do is you take this delta double prime, which is mu 1 psi 1 psi 1. So, this is a rank 1 operator, right, positive operator, positive semi definite operator, rank 1, okay. And you take this gamma double prime, you define it as gamma prime plus L is equal to 2 to rank of delta mu L psi L psi L. So, I have taken 1 out of it, okay, right. So, this is my gamma double prime, okay. So, if you look at it, you see that this is again a valid covariance matrix, bona fide covariance matrix. Why? First of all, this is positive definite, you can show that, and then the reason for which gamma prime is a covariance matrix, for the same reason this will also be covariance matrix, because if you add this plus iota by 2 omega, because gamma prime plus iota by 2 omega greater than equal to 0, this as a whole will be greater than equal to 0, okay. So, this is a bona fide covariance matrix, okay. And what are the properties of this? So, this covariance matrix is such that you see that gamma, the original one, is greater than equal to gamma prime. Why greater than equal to? Because gamma prime plus delta, this will be your gamma. I have taken one rank 1 operator from here. So, therefore, this has to be the case. Okay. And then of course, gamma is not equal to gamma tilde, because already gamma is not equal to gamma prime. So, therefore, this has to be the case, and then gamma minus gamma double prime, which is equal to delta double prime, it is a rank 1 operator. So, you see that even if your gamma prime, even if this is not, this is, so this gamma is a PPT covariance, but not minimal, and even if in that case you will have some gamma prime less than equal to gamma and which is not equal to gamma, this difference which is delta, it may be more than rank 1, but I can make it a rank 1 in this way. Okay. So, therefore, I will not concentrate on gamma prime, I will concentrate on gamma double prime. So, that this will become a rank 1. So, when I discuss about minimal PPT, it is enough to consider this to be a rank 1 operator. Okay. So, using this one can prove this notion, one can prove that this this. So, using this property that you take the minimal covariance matrix, and in which case you can always take it to be rank 1. I mean, if it is not minimal, if it is covariance, PPT covariance, but not minimal, you can always take it to be rank 1. Okay. So, with this notion of this PPT covariance, minimal PPT covariance, and then this rank 1 operator, you can show that this for any, this I have already mentioned, any 1 cross n mode Gaussian state, rho a b t a greater than equal to 0, same as rho a b is separable. So, this again, this proof is bit slightly lengthy, but you can start from here, that yeah. I mean, basically the idea is that because of this thing, that you can take it to be rank 1 if it is not PPT covariance, if it is not minimal PPT covariance. So, the idea is that you start with this rho a b, okay, and then what you do is you can write it as something, I mean maybe I will call it as like rho a comma b minus c. Okay. So, this is the, basically this is a reduced state of this one plus gamma of c. So, you take a part of your, a part of the this part p of b, okay. This is my phase space for the b part. From here you take a part p c's, okay, and you can show that if this is the case, if it is separable, of course, you can prove that, but if this is the case, then you can show using this notion of covariance and PPT covariance and minimal PPT covariance, that ultimately you can write down the covariance matrix in this form. Okay. So, this tells you that basically now it is, you know, kind of separable between this and this. Now, you concentrate on this part only, forget about this part, because this is anyways it will make it separable. Now, you concentrate here again. Okay. So, this you can make because ultimately you have this difference as a rank 1 operator. So, this corresponds to something like a rank 1 or let us say mode 1. Okay. Now, here again you do the similar thing. So, you break it down, you take away another mode. single mode, so on and so forth. So, basically what you will have is ultimately you will see that this can be ultimately written as basically gamma A plus gamma B, something like this. Okay. And this will tell you that this is separable. So, this is what the proof is. I am not going into the details of the proof, but this is what it will be. Okay. And finally, the this so I will just mention this. So, they have given, of course, they have written one example, but in principle this can be family of examples, not just one. Okay. So, you take this. So, this is the 2 cross 2 mode case, I mean 2 mode versus 2 mode. So, let me write it down like this. Okay, so this is my x1, p1, x2, p2, x3, p3, x4, p4. So, this all will form my B subsystem and this all will form my A subsystem. Similarly, here x1, p1, x2, p2, x3, p3, then x4, p4. So, this will form B subsystem and this will form A subsystem. Okay. Right. So, here you take this as your covariance matrix 2 0 0 0 1, then 0 0 0, then 0 1 0 0 0 0 0 minus 1, yeah, 0 0 2 0 0 0, then minus 1 0, then it is 0 0 0 1 0 minus 1 0 0, then it is 1 0 0 0 0 2 sorry 1 sorry this is 2, this is 0 0 0, then this is 0 0 0, this is minus 1, this is 0, this is 4, this is 0 0, and then this is 0 0 minus 1, this is 0 0 0 2 0, then this is 0 minus 1, and then this is 0 0 0 0 0 0 0 4. Yeah. So, you see all the entries are integers and this they have taken keeping in mind that numerically if you want to figure out its separability etc., then there might be some numerical errors also. Have you in case you would have taken some fraction, then there would have been some chance of numerical error, more numerical error. So, that is why they restricted here for integer entries, and you see that this is a you can prove that gamma is positive, all the eigenvalues of gamma are non negative, I mean are positive. This is one. This you can prove, it is not difficult. I mean, you know, the only thing is this part of the matrix where you have some negative one. I mean, if these were all 0 except these two, if these were all 0, then this is of course positive definite matrix, but you can prove that this is indeed a positive definite matrix. Number 2, gamma plus, and this is a 2 cross 2 mode case. So, that is why it is 8 cross 8, gamma plus iota by 2, this is greater than equal to 0, this also you can prove. Okay. Right. And so, therefore, this is a, so this means that gamma is a bona fide covariance matrix for a 2 cross 2 mode Gaussian state. I could have taken some other state also, but in principle I can take it to be covariance matrix of a 2 cross 2 mode Gaussian state, right. This I can always take, right. And now you can prove that gamma plus iota by 2 omega tilde, this is also greater than equal to 0. Okay. This you can prove here. So, this means that so this is a 2 mode Gaussian state, this is rho a b, this is 2, this is 2. So, this means that rho a b, let us say T a is greater than equal to 0, because this condition, okay, this is a state. Okay. Right. Now, one can also prove that, so this means that ultimately that gamma is a PPT covariance matrix, okay, because this is satisfied, this is satisfied. So, therefore, this is a PPT covariance matrix. You can prove that this real part of this union real part of this tilde. So, this is the null space of gamma plus this one, and this is the null space of real part of, okay. So, this spans the entire phase space, that also you can prove. Okay. So, this means what? What does it mean? It means that gamma is a minimal PPT covariance matrix, right, because of this thing. You remember our, I think, proposition 3, it tells you that if this is the case, then gamma is a minimal PPT covariance matrix, okay. Right. Now, for a minimal PPT covariance matrix, we have seen that that its separability means, now what you can prove is that this gamma is not equal to gamma of A plus gamma of B. So, gamma of A is basically your gamma of rho A, and this is gamma of rho B. Okay. So, this you can prove that gamma is not equal to this thing, and this means, so you see, because this is minimal PPT, so this means that rho A B is entangled, because if this for a minimal PPT gamma, if gamma is equal to this means that rho is separable, but and this is if and only if condition, and this because this is a Gaussian state. So, this because this is the case, this one can check that gamma is not equal to this one. So, therefore, rho a b is entangled. So, you see that you have an example of a 2 cross 2 mode Gaussian state which is PPT and it is entangled. So, this is a bound entangled state and this is the Gaussian state. Okay. So, they have given other how to construct such kind of gamma, but yeah, that is okay, that is fine. So, with this I will basically complete it. So, what I was planning to do is first of all the Gaussian channels. So, under so what sort of channel action will take Gaussian states to Gaussian state, that one can also classify into attenuator and then amplifier and all these things one can do. And then
Would a channel also correspond to a waveguide of the board?
yes, in some sense, yes, yes, yes,
Waveguide has anything.
yes, anything, yeah. So, what so that is what I was having planned, that I will also consider these channels and then some of these capacities, okay, of let us say the Gaussian channels, okay, classical capacity, quantum capacity, like the one which mostly the Seikat Guha has done. Okay. But maybe for the timing that is enough. So, if I have energy and time in July, August, something like that, then I will again continue this. Okay, thank you.